Hello, everyone. Today we will talk about noise analysis in analog communication systems. We will start by talking about double sideband suppressed carrier receivers. So, as you know, our DSP-SC system, as we discussed before, is going to be subject to additive noise at the receiver. So this is the receiver, and we model the noise as being added to the incoming modulated signal at the receiver front end. Here, HR of F is the filter that stands for the equivalent effects of all RF front end components. And X of T is the signal that contains the filtered signal coming in, as well as the filtered noise. And as you know, the receiver structure is basically a mixer followed by low-pass filtering. Of course, you can implement this through various sophisticated mechanisms like a Costas loop, etc. But at the end of the day, it breaks down into generating the carrier and mixing it with the incoming signal and low-pass filtering it. Okay, so let's first compute the baseband SNR. We defined this last time as the ratio of the message power to the noise power in the message bandwidth. So the signal power is the expectation of the modulated waveform, which we can represent as M of t AC cosine WCT. And if you square it and take the expectation, you will find, well, if this is PM, P sub M, and this is clearly a half, we have this as the message power. Alternatively, you can think of it as integrating the power spectral density. Not alternatively, actually. How do you find PM? How do you find PM when you, here, essentially we use expectation of M squared, which is our M of tau, at tau equals 0. The autocorrelation evaluated at 0. Alternatively, this power can be found by integrating the power spectral density of the message waveform if you have that available. Now, SNR baseband, talking about the average power of the noise in the message bandwidth at the receiver input. Well, the message bandwidth is U, and AWGN, additive white Gaussian noise, has constant PSD and not over 2. So n not over 2 times 2W gives us n not W. And SNR baseband is computed as AC squared PM over 2n not W. Now let's compute the output SNR. Okay, so now we will model HR as an ideal bandpass filter with bandwidth 2W. Okay, so how about the actual noise? How does it look? Okay, the noise is filtered by this HR, H sub R of F. And the noise has flat spectrum at n not over 2. Therefore, the noise PSD looks just like this shape. It's just that it is scaled by n not over 2. So the integral over the noise PSD is 2W times n not over 2 times 2, which gives us 2m not W. So notice that this is twice the noise that we computed for baseband SNR. for base, yeah, right. The SNRB computation had noise in the baseband, which is M naught W. Noise in passband has power that is twice that. Okay. Now, how about the signal power at the output? Well, by the way, it is worthwhile thinking about the noise in terms of its in-phase and quadrature components, because notice that this is band pass noise. Okay. Whenever we have a band pass signal, as we discussed last time, we can represent it as the in-phase component times cosine WCT minus the quadrature component times sine WCT, where WC is some frequency that you can choose from within the passband. Ideally, of course, it is equal to our carrier frequency for convenience. Okay, we can represent this as the real part of some complex signal. So this is again for convenience. We're talking only about real signals in the system. However, we can always represent our real signal in terms of its in-phase and quadrature components as if there is a complex signal and our signal is the real part of it. So in that sense, we convert our bandpass noise signal into a low pass or baseband complex signal. We will make use of this a lot, just like we've used it in the past. Okay, now if you look at the PSDs of these in-phase and quadrature components that are low pass stochastic processes, as we showed before in our previous lecture, they span a bandwidth 2W across 0. Okay, and the height of the PSD is N naught. Why? Because the two components from FC and minus FC come together and add on top of each other, and naught over 2 is multiplied by 2. Okay. So, and also they have equal power, both Ni and Nq, and this is equal to the power of the original passband noise. And we can compute it from the figure as 2 N naught W. So it's the same computation, but we just did it using the in-phase and quadrature components. It's the same computation that we did in frequency domain here in the passband directly. And alternatively, doing the same thing in baseband. Now, let's switch back to time domain. In the time domain, we have our incoming signal. We are ideally representing it as if it's the same as the modulated waveform. In practice, of course, it's going to be subject to attenuation and possibly other factors. So this is the signal component, and this is the additive noise component. Notice that only the in-phase component of our noise is adding on top of the signal in phase, as the phrase suggests. And the quadrature component is going to be orthogonal to our modulated waveform. Okay. So now let's consider the mixer. The mixer is going to multiply this thing by twice cosine WCT, which will pick up the first term, this term. Oops. strange. It will pick up this term. And since this cosine and the sine are orthogonal, we get rid of the quadrature noise components. Of course, we're going to have high frequency terms that are going to be eliminated by the low pass filtering. And the result is AC M of t plus the in-phase component of the noise. Okay, notice that this demodulated signal is in baseband. So what is the signal energy in the output? The output is composed of signal plus noise. The signal energy in the output corresponds to this component. It's AC squared PM. And the noise energy in the output is 2N not W. Remember, we already computed this before. Okay, so this is the output SNR, AC squared PM over 2N not W. Notice that the baseband SNR is identical to this. In the baseband SNR, our signal power was half of AC squared PM, and our noise power was N naught W. So the ratio is exactly the same as this SNR O. Now we define something called a figure of merit for comparing the SNR out with SNR B. I mean, we define the figure of merit as the ratio of SNR O to SNR B, and this figure of merit is going to be used to compare different modulation and demodulation schemes. For double sidebands, the figure of merit is 1. Now, well, relative to the double sideband, let's see how the other analog communication structures rate in terms of the figure of merit. Let's consider SSB first. The difference of SSB is that, as you know very well, it uses half the bandwidth. So again, we're thinking about a real valued message waveform, and it's SSB modulated. Again, at the receiver front end, it gets filtered after noise is added. Okay, noise is added at the receiver front end, and noise and signal both get filtered together. And the demodulator consists of, again, a mixer. Right, so our signal structure in SSB is going to be a little different because we have a in-phase component and a quadrature component. That is, we have a sine and a cosine term. So, so then you may say both the in-phase and quadrature noise components are going to matter for this case. Okay, well, let's see if this is going to reduce the figure of merit below 1 or not. Well, what is the noise PST that comes in, the white noise, and not over 2 as before. And M of t, again, M of t, let's not make it right. M of t is a signal with PST as before. We're using the same thing with the power P sub M. Let's start by computing SNRB. What is the power in the input signal? We can get it by, let's do the time domain, use the time domain approach, because we already have the expression for the modulated waveform as such. So we'll simply take the expectation of S of t squared. So expected M of t squared expected cosine WCT squared. Well, cosine WCT is simply a deterministic signal. That is why it comes out. I mean, the expectation is split into two. Also, the sine and cosine are independent, orthogonal. So that's why, well, at this moment, we're not using it. We will use it later on. So we have the, inside this S squared, we have two additive terms, and the two terms are expanded here. Okay, so now, and there is a cross term, right? Cross term. So the orthogonality of sine and cosine are going to come into the picture to eliminate the cross term. Okay. Now we showed before that M hat is the Hilbert transform of M, which is basically, which corresponds to an LTI filtering operation. And the filter is J signum of F, negative J signum of F. And we know that when wide band stationary signal goes through an LTI filter, the power spectral density is multiplied by the filter magnitude characteristic squared. So from that, we can find the output PSD, the PSD of M hat in terms of the PSD of M as the following. And of course, when you square the signum, you get unity. So that's why M hat has the same power as the message. Okay, so the message M and its Hilbert transform have equal power, which is not surprising at all. All right, so how about SNRB? We computed SB. Why? Because this is PM, this is 1/2, this is equal to PM, this is equal to 1/2. And therefore we have AC squared over 4 PM. Okay, we got this. And how about the noise power? Now, this is interesting. No, I mean, this is not interesting yet, I think, because we're talking about the noise power in the message bandwidth. Remember, this is SNRB. I think SNR out is more interesting. SNRB is simple. It's the same exact computation as double sideband. So we have N naught over 2, of course, AWGN, PSD. Okay, and we multiplied by the message bandwidth. Why? Because the message, as we said, is like this. Okay, W, but you know, the total bandwidth here is 2W, and the noise is white noise and not over 2. So we are the message bandwidth that we're interested in is this 2W. Okay, so 2W times N naught over 2 is N naught W. So we're ready to compute SNRB, and SNRB turns out to be AC squared PM over 4 N naught W. So how does it compare with the SNRB of double sideband? Let's check. SNRB of double sideband was equal to the SNRO of double sideband. It's AC squared PM over 2 N naught W. Here we have AC squared PM over 4 N naught W. Oh, the incoming SNR is half as much. Okay, but incoming SNR doesn't mean anything. It's just something that we define as a benchmark. What's important is the outgoing SNR and its ratio to the output SNR, it's ratio to, and it's ratio to the input SNR. So let's compute the output SNR. We have this modulated waveform PSD. Notice that we are using a filter that is not symmetric around FC, because in this picture we are focusing on lower sideband modulation. FC is here, okay, and this is FC minus W. So if this had been double sideband, our filter would have been two-sided, right? It would go from, FC would be here, it would be symmetric around FC. This is the double sideband case. But we don't have this situation. We don't have this situation. Our filter is half as wide and it is not symmetric. So the filtered noise is going to have half as much power as double sideband. So let's consider this filtered noise as a pass band, as a band pass signal with its in-phase and quadrature components. Again, by the theory that we reviewed earlier, the in-phase component and the quadrature component have both equal power and they are equal to the noise power itself. And we are talking about a bandwidth W here and another bandwidth W here, and the PSD has height and not over 2. So it comes to and not W as a total power. Notice that this power is half as much as it is in double sideband. Okay, so now let's consider the demodulation of the message. The modulated waveform that comes to us has M of t cosine WCT, M hat of t sine WCT. It is lower sideband. Okay, so this plus sign is consistent with that. Plus the bandpass noise. Now at the mixer, now remember we have essentially two mixers, right? Because we have an in-phase branch and a quadrature branch when we're trying to decode. I'm trying to demodulate SSB. We're not decoding anything yet. We will be decoding things when we talk about digital modulation. So AC over 2 M of t plus Ni is the cosine component. And M hat minus NQ is the sine component. Actually, I made a mistake when I'm talking about the two branches. Of course, we're doing demodulating SSB. Now we're not demodulating QAM, okay? So we only need this component. We only need one mixer. So sorry about the earlier confusion. So we only need one mixer, and because we're not sending independent messages along the in-phase and quadrature branches. Okay, if we were doing QAM, that would be a different story. But this is SSB. So multiply by cosine, and you find AC over 2 M of t plus the in-phase noise plus high frequency components. Therefore, we get AC over 2 M of t plus the in-phase component of the noise. Wow, today I'm doing interesting polygons. Okay, so all right. Now, what is the difference of this from double sideband? In the double sideband case, let's see. In the double sideband case, we had AC over AC M of t plus Ni. Now we have AC over 2 M of t plus Ni. So the signal power in the demodulated waveform is going to be half as much. Actually, 1/4 as much. Okay, AC squared over 4 PM. And the output noise is N naught W, which is half as much as the double sideband case. So when you compute SNRO, it is AC squared PM over 4 and not W. What is SNRB? SNRB is AC squared PM over 4 and not W, which is exactly the same. So both SNRO and SNRB are lower than the double sideband case, resulting in the same figure of merits as in the double sideband case. Okay, so in terms of SNR, there is no advantage of using SSB over double sideband. It turns out they have the same figures of merit. SSB still dominates double sideband, provided it can be used. Remember, it has to have a DC null. The signal has to have a DC null. But if you can use SSB, it's still a better idea due to its smaller transmission bandwidth. Okay. So the next topic that we're going to discuss is conventional AM. But it appears that that is next time. So next time we will talk about noise in conventional AM with envelope detection. Okay.